Okay, I'd like to finish up section 10.2 here. We're talking about surface area, and just so you know, every single one of these problems, remember, has to do with t. It has to do with t. So whether I'm taking a derivative, or whether I'm integrating, or finding an arc length, it's all about t, right? And so the same thing is going to be true here with the surface area problems. It says in the same way for arc length, we can obtain a formula for surface area. If the curve C is given by the equations x equal f of t and y equal g of t, parametric equations there, for when t is ranging between alpha and beta, and that's rotated about the x-axis, then the area of the resulting surface is this integral here. Okay? So let's see, in problem 9, we want to show that the surface area of a sphere of radius r is 4 pi r squared. Okay? Now, to do that, we're going to use the parametric equations x equal r cosine t and y equal r sine t. So that'd be a circle. And how I know that is because if a and b are the same number, you got a circle there to talk about ellipse. Now, by the way, these parametric equations are going to be very important to us in the next section. Okay, so that'd be ones that we should have memorized. So, so I've got a circle of radius r, and I'm rotating, let's see, the interval from 0 to pi about the x-axis. So, okay, if t is pi, cosine pi is -1, and, all right, excuse me, let me start with 0. If t is 0, cosine of 0 is 1, and sine of 0 is 0. So x would be r, and then 0, you'd be starting there. And then if t is pi over 2, cosine pi over 2 is 0. And then sine pi over 2 is 1, so you have r. Okay, so it'd be right there next. And then if t is pi, cosine pi is -1, so you have negative r for the x value. And then sine pi is 0. Okay, so that'd be ending here. So I would have traced out this half circle going right to left there, so something like that. Okay, and now I want to rotate that about the x-axis. So if I rotate that about the x-axis, I'll create a 3D object, which would be a sphere, and the surface area of the sphere is 4 pi r squared. So let's show that. Well, again, everything about my integral is going to be in terms of t here. So t is ranging from 0 to pi, and I got 2 pi times y is r sine t times the square root of dx dt squared. So that's going to be negative r sine t. I'm squaring that. Plus dy dt squared. So that'd be r cosine t squared. And stick a dt at the end. Okay. 2 pi times the integral going from 0 to pi of r sine t times the square root of, now r squared, that's in common these two groups, right? If I square this, I got r squared times cosine squared t, and there's negative r squared, the same as r squared times sine squared t. So r squared is in common those two things there. Let's go ahead and factor that out. We got sine squared t plus cosine squared t left over in the integrand. Underneath the radical there. That's 1. Okay, the square root of r squared is r. It's actually the absolute value of r. But r is a positive number anyway, right? R is the radius of the circle. You can't have a negative. And r times r is r squared. 2 pi r squared, that's a constant. I can bring that outside the integral. Times the integral going from 0 to pi of sine t dt. Okay, so that's going to be, when I integrate sine t, I get negative cosine t. I'm going from 0 to pi. And then when I plug in the bounds, cosine pi is -1, so the opposite of -1 is 1. I get 2 pi r squared times 1. And then minus, when t is 0, I get 1 there, so it'll be minus a negative, means plus 2 pi r squared times 1. Okay, and that'd be 4 pi r squared. That's what I get. That's what the surface area of a sphere is. Okay, so that's problem 9. And in problem 10, let's see, it says the cardioid shown below has the parametric equations x and y. T is ranging from 0 to 2 pi. To completely trace out this curve one time. If the curve is rotated about the x-axis, find the resulting surface. Okay, so of course I'm going to use this formula, and I got to find dx dt squared plus dy dt squared. That's going to be this work right here. Just the reason why I'm not setting up an integral is because I don't have thousands of integrals all over the place. So just once I've got that all simplified, then I'm going to go ahead and give my integral here. And also we'll go ahead and simplify y as well. Okay, so let's see, dx dt squared plus dy dt squared. So when I differentiate x, I get negative 2 times sine t plus 2 sine 2t. I'm squaring that. And then plus, it's going to be dy dt squared. That's 2 cosine t minus 2 cosine 2t squared. Okay, so we got to simplify this. Now, if I were to square out negative 2 sine t plus 2 sine 2t, so negative 2 is in common to these two groups. Right, so let's go ahead and factor that out of the whole thing. I'm factoring out a negative 2. Negative 2 squared is 4. And also right here, I've got 2 squared is 4. Okay, so I'm going to be foiling out sine t minus sine 2t, and then cosine t minus cosine 2t. Okay, we're going to FOIL out both those. So when I FOIL out the first one here, sine t plus, sine t minus sine 2t, that'd be sine squared t minus 2 sine t sine 2t plus sine squared 2t. Okay, and then when I FOIL out cosine t minus cosine 2t, I'm going to have cosine squared t minus 2 cosine t cosine 2t, then negative times negative is positive, so it'll be plus cosine squared 2t. Okay, 4 has been brought out the whole thing. So the next thing that I do is sine squared t plus cosine squared t, that's 1, right? And then sine squared 2t plus cosine squared 2t, that's 1. Sine squared of an angle plus cosine squared of the same angle is always 1. So I got 1 plus 1, then minus 2 times, let's see, I'm factoring out this negative 2 here from these two parts. So the leftover would be cosine t cosine 2t, and then plus sine t sine 2t. Okay. So then 2 plus 2, that's what I get there. Then if I factor out a 2 from these two groups here, I got 2 minus 2 times all this. 4 times 2 is 8. Times 1 minus cosine 2t cosine t plus sine 2t sine t. Okay. Now the next thing is because I'm going to have to integrate this, I don't want a product here. It's going to be easier for me to deal with the product to sum formulas. Okay, we saw those in section 7.2. And let's see, for cosine 2t kind of times cosine t, that'd be this guy right here, I'm getting 1/2 cosine of 2t minus t is t, and then plus cosine of 2t plus t is 3t. Okay, and then I'm going to be adding. The sum and difference formula for sine 2t sine t is up here. Now the only difference between these two is I'm changing this to a minus sign, whereas it's a plus sign down here with with cosines. So I'm going to have, the same thing here, only it's going to be a minus sign. Okay? And I get 1/2 times both those. All right? So the next thing that I do is I got 1 minus 1/2 times cosine t minus 1/2 cosine 3t. Now I am subtracting, I'm subtracting a negative, right? Because the negative is going to come into there and then also come into there. So I'd be adding 1/2 cosine 3t. So negative 1/2 cosine 3t plus 1/2 cosine 3t, those are gone. Okay, and then here's 1 minus 1/2 cosine t, and then we got a minus, it's going to come in there, 1/2 cosine t, that's minus cosine t, 1 minus cosine t, times 8. Okay, so that's what this guy simplifies down to be. Okay, now also in this formula here, we've got y. Okay, so let me go ahead and simplify y. Here's y. And I'd like to have it be, just single angles. I see there's be a double angle here, right? You got sine 2t. Sine 2t, that's same as 2 sine t cosine t. So I got 2 sine t, that's in common these two groups. Let's go ahead and factor that out of the whole thing. And I have 1 minus cosine t left over from that. Okay, so now I'm ready to plug this stuff in my integral. Now, the reason I'm going from 0 to pi is because this curve can be completely traced out one time on the interval 0 to 2 pi. Okay, I don't want to go 0 to 2 pi though, because if I go 0 to 2 pi and I'm rotating this about the x-axis, that's going to be double the surface area. I don't want double my answer, right? So let's just take the top half of this cardioid and we'll rotate that about the x-axis. Okay, so I'm going 0 to pi, and then inside the integral, I'm going to have 2 pi times y. Y is 2 sine t times 1 minus cosine t, that's there. Okay, and then times the square root of dx dt squared plus dy dt squared, that is right here. Okay, so the square root of 8 is 2 root 2. And then I got the square root of 1 minus cosine t. And then dt. Okay, so the next thing is here's 2 times 2 times 2, that's 8. Pi root 2, go ahead and factor that out of the integral. And times the integral going from 0 to pi of sine t times 1 minus cosine t times the square root of 1 minus cosine t. That'd be 1 minus cosine t to the 3 halves. Keep the base and add the powers. Okay, and what I'm doing is I'm setting myself up for a u substitution. Okay, if I let u be equal to 1 minus cosine t, du is sine t dt, okay, which I've got a sine t dt at the end of this integral. I'll be able to knock out that part. And so we would be integrating 1 minus, we'd be integrating u to the 3 halves power, right? So that'd be u to the 5 halves times 2 fifths, 8 pi root 2, that's me in front of the integral, right? So that's me in front of the antiderivative. And go ahead and replace u. U is 1 minus cosine t. We're going from 0 to pi. And so now when I plug in my bounds, let's see, cosine pi is -1. And cosine of 0 is 1. So I'll be subtracting 0 there. But 1 minus a -1, that's 2. Okay. So 2 to the 5 halves times 2 times 8 times root 2. Root 2 times 2 to the 5 halves, that's the same as 2 squared to the 1/2. 2 to the 1/2 times 2 to the 1/2, that'd be 2. So I'm going to have 8 times 8 times 2, which is 128. Okay, we got pi up top, and 5 in the denominator. So the surface area then of this cardioid, it looks like when I wrap this around the x-axis, or when I spin it around the x-axis, it's going to create like an apple-looking thing. Okay, so the surface area of that cardioid, or that apple-looking thing, is 128 pi divided by 5. Okay. All right. So there's a lot of information here with parametric equations. I get that. Again, everything has to be in terms of t, right? So when we set up our integrals, or when we find a derivative, it's all about t. It is all about t. I don't want to mix and match x and y and stuff like that. Okay, it's all about t. So be sure that when you get your integral, everything about the integral is in terms of t there, okay, including the bounds. So, all right. The homework is on page 679. You guys should be able to have a go at those problems there when you get a chance. And now in the next 2 sections, we're going to talk about polar equations and polar coordinates in calculus. Okay, so we'll hit that in the next video.